back. In this screencast, I want to talk a little bit about decimals just to kind of illuminate a little bit, I hope, some of what the authors of your text were saying about decimals. Let's talk a little bit about decimals. For all decimal numbers D is some integer plus an infinite sum as k goes from 1 to, not that the sum is infinite, but that the sum goes from k equals 1 to infinity of some a sub k over 10 to the k, where b is some integer. That is to say, every decimal number d can be expressed as its whole number parts plus all of the sum of all of its decimal numbers after the decimal point, the decimal digits in their place values, we add them up all together. This is the whole number part. This is all the stuff that happens after the decimal point, which should be pretty straightforward. So let's see if this makes any sense. If the a sub k's are chosen from the set of digits, and there are 10 in base 10, then that sum, the sum of the a sub k's over 10 to the k, and just to be clear, that's a1 in the 10ths place, that's a2 in the 100ths place, and so on. That number converges to a real number somewhere between 0 and 1. Somewhere between 0 and 1. So the proof of this is fairly straightforward. We're going to notice that the a sub k's are non-negative. So the sum is non-negative. What does that do? That establishes this end. That establishes that we're not going to get a negative sum out of all of this. Now, for the other part. Also notice that the desired sum is less than 9/10 plus 9/100 plus and so on. This is 0.99999999999. Well, that's a geometric series that converges to 1. So if you choose all 9s, you're in the desired interval. And if you choose any of these to be less than 9, then the desired sum is less than 1, and you're in this interval. So we're done. We're done. That's to prove this. Every real number has a decimal representation. There is no real number that you can imagine that you cannot type into a TI infinity calculator. Proof. If we prove the theorem for the interval from 0 to 1, we're done. Why? Because every decimal number has an integer part before the decimal point and then something from here after the decimal point. So if we can prove it for the part that's after the decimal point, then we're done, because every other real number is one of those plus an integer. So we're going to let x be in the interval from 0 to 1. we can always choose a sub 1 from our set of digits with a sub 1 over 10 less than or equal to our number x less than a sub 1 plus 1 over 10. Uh, in other words, whatever our decimal number is, whatever our real number is, it falls between two of the point whatevers, 0.3 and 0.4, 0.8 and 0.9. 0.9 and 1.0. We can always trap the real number between two of those decimals. Well, then, if you subtract off a sub 1 over 10, that is in the interval between 0 and 1/10. And we repeat the process. We trap what remains between two numbers rounded to the nearest 100th, and we continue and continue and continue. So how do we know that this can go the way we think it does? Well, if we subtract off n decimal places, right? That's what this is. We've subtracted n decimal places. What we have is still a positive number, right? We've taken x and we've lopped off not quite all of it. That's a at least a non-negative number. And that's less than or equal to 1 over 10 to the n. Each time we get within a smaller power of 10, but we're still within a power of 10. Well, in Calculus 1, they taught us that if this has a limit of 0 as n gets large, and this has a limit of 0 as n gets large, then the squeeze theorem says that this has a limit of 0 as n gets large. And so by the squeeze theorem, this goes to 0. Well, why do I care that this goes to 0? Well, it means that x becomes this sum as n goes to infinity. That's exactly what we wanted, and so we're done. Every real number has a decimal representation. Every single one. We can trap it. As for which decimals are rational and which are irrational, we'll talk about that when we gather. For now, this is enough. We'll see you soon.